All right, so we're going to do the walkthrough for the derivatives of exponential functions homework. So um, for this first one, we just have y equals e to the 2x. And since we know that the derivative of e to the x is just e to the x, we can use the chain rule on this and treat it as if it is y equals e to the u, where u is equal to 2x. So we just need the derivative of y equals e to the u, dy du, which will be e to the u. And we need the derivative of u with respect to x, which will just be 2. And so our final result is the product of those two things. That'll be, we'll write dy dx is equal to 2e to the u. Well, since u was 2x, we'll say 2e to the 2x. Right? And so if you want to try and get used to doing these quickly, you can just keep the same e to the 2x and then multiply it by the derivative of the 2x, which is how I'll normally do those in my head. All right, so for this one, it's the same idea. It's e to the x squared plus 1. So the derivative should just be e to the x squared plus 1 times the derivative of x squared plus 1, which is 2x. So that's really our final answer. If we need to break it down further, if you're having trouble doing that, it's just y equals e to the u, where u is x squared plus 1. So the derivative of e to the u, right, dy du here, dy du is e to the u, and du dx is just 2x. So multiply 2x by e to the u, or u equal to x squared plus 1, and you get the same thing. Right? You get 2x e to the x squared plus 1. And either one of these answers, with the 2x in the front or the 2x after the e to the x squared plus 1, are fine. But if you do put it afterwards, make sure it's in parentheses and clearly not part of the exponent. For e to the sine x, we're just going to treat this as y equals e to the u, where u is equal to sine of x. So dy du is still e to the u, just like it will be every time. And du dx, well, the derivative of sine x is cosine x. So we'll just multiply those together, which gives us cosine x times e to the u. Well, u is sine x, so e to the sine x. For this one, e to the x cubed minus cosine 2x, we'll do the same thing. We'll treat this as if it is y equals e to the u, with u equal to x cubed minus cosine 2x. So dy du is once again going to be e to the u, and du dx will start off being 3x squared using the power rule. And then the negative cosine 2x, negative cosine 2x is like negative cosine v, where v is equal to 2x. So we need the derivative of each of those. Well, the derivative of negative cosine v, the derivative of cosine is negative sine, so that's just going to be sine v. And the derivative of v will just be 2. So we're going to end up multiplying the 2 times the sine of v, or the 2 sine 2x. We'll get plus 2 sine 2x. And so now our final result here should be e to the x cubed minus cosine 2x times 3x squared plus 2 sine 2x. And for e to the tangent cubed x, this is going to be a chain rule within the chain rule. Our outermost function going on here is e to the u, where u is equal to tangent cubed x. Well, it's easy enough to find dy du. dy du is just e to the u. But du dx, to find that, we're going to have to break this down a little further. U is equal to tangent is equal to v cubed, where v is equal to tangent x. So we're going to reapply the chain rule here, right? Because the larger function, the outer function on this for the chain rule is the cubed, where we have tangent being cubed. So u is going to be v cubed, and v will be tangent x. So now we'll find du dv, which is 3 v squared, and then we'll find dv dx. The derivative of tangent is secant squared. So we just need to now multiply all three of these things together. And as we do that, we'll replace the u's and the v's with what they are in terms of x. So e to the u will be e to the tangent cubed x, because that's what u is in terms of x. And then we have 3v squared, so I'm going to throw the 3 out in front. And then our v squared, well, v is tangent x, so this will be tangent squared x. And then dv dx is secant squared x. And so there's our final answer. And for the rest of these, we're going to have a different rule, not just the e to the u, but we're going to have a to the u. So we want to remember that, if we have a to the x, the derivative of a to the x is a to the x times the natural log of a. Right? This is the base rule that we're going to be using for each of these, basic rule. But of course, these are all going to be chain rule applications. So this is like y equals 2 to the u, where u is equal to 3x. So we'll use the rule for a derivative of a to the u, or a to the x, for the first part. So dy du will equal 2 to the u times the natural log of 2. And then du dx here is just equal to 3. So our final answer should be the product of those two things. It should be 3 times 2 to the u, where u is 3x, times the natural log of 2. Same idea here. This is y equals 3 to the u, where u is equal to 1/4 x. Well, dy du is just going to be 3 to the u times the natural log of 3. And du dx is just going to be 1/4. So when we multiply this together, we've got 1/4 times 3 to the u, where u is 1/4 x, so 1/4 x there, and then times the natural log of 3. And that should be dy dx. For 4 to the secant x, we're just going to apply that same rule. This is y equals 4 to the u, where u is equal to secant x. So dy du is just 4 to the u times the natural log of 4. And du dx, we have a rule for secant x. Du dx is just secant x tangent x. So when we multiply dy du times du dx, we end up with 4 to the u, where u is secant x, times the natural log of 4, times secant x tangent x. And that should be our final derivative. There's just 2 more to go here. This one is, again, y equals 5 to the u, where u is equal to x squared cotangent x. While dy du is just going to be 5 to the u times the natural log of 5. But du dx is a product of 2 functions. So when we find the derivative of x squared cotangent x, we're going to have to use the product rule. So we'll start with the first function, x squared, and we'll multiply it by the derivative of cotangent. Well, the derivative of cotangent is negative cosecant squared. And then we'll add to that the cotangent x times the derivative of x squared, which is 2x. So that's just our product rule. Now we'll multiply it all together. We've got 5, I'll put my dy dx out here. Dy dx is 5 to the u, where u is x squared cotangent x. And we'll multiply that by the natural log of 5. And then we'll multiply it by our du dx. I'm going to write the 2x cotangent x first, minus x squared cosecant squared x. And if you choose to factor an x out of that, that's totally fine, but I don't particularly see the need to, so I'm just going to leave it like this. And here is our last one, 10 to the cosecant 10x. So this is y equals 10 to the u, where u is equal to the cosecant of 10x. Well, the derivative of 10 to the u with respect to u should be easy enough. dy du is just 10 to the u times the natural log of 10, just what we've been doing for each of these. But du dx, we're going to have to use the chain rule because that's the cosecant of a function. So we'll say that u is equal to the cosecant of v, where v is 10x. And so now we will we'll take the derivative of each of these separately. So du dv, well, the derivative of cosecant is negative cosecant cotangent. So we have negative cosecant v cotangent v. And then we have dv dx, which is just 10. So if we multiply all this together, first off, way out in the front, we're going to have a negative with a 10. So we're going to have negative 10 times our 10 to the u, so 10 to the cosecant 10x, times our natural log of 10. And we've already dealt with the negative sign and the 10, so now we just have cosecant v cotangent v, so that'll be cosecant 10x, because v is 10x, and cotangent 10x. And that should be our final answer. And that's the end of the derivatives of exponential functions assignment.